All right, so let's do another one real quick. We have NH3, ammonia. So with ammonia here, first thing we're gonna do is we're gonna count how many valence electrons we got. Nitrogen has 5, hydrogen has 1 each, so we've got a grand total of 8. You don't need to do this, it's just something I do. It helps me keep my head straight of how many electrons we have so I don't forget. So this is just me notating, but you can do it, whatever. So it's 8 valence electrons. What we're gonna do next is we're gonna take our nitrogen and we're gonna put our hydrogens around it first and foremost where they're as evenly spaced around the central atom as possible. So we have a 120, 120, 120. That's as far as we can get, even in a 3D world from each other. And now the next thing I'm gonna do is I'm gonna count how many electrons I have down. So I've got 2, 4, 6. I've got 8 total. Well, let's figure out what we're gonna do with that. Hydrogen can only hold 2, a 1s2, can only hold 2 electrons. So this guy, and this guy are all full. Nitrogen, however, can hold 8. You know, remember the second energy level, those guys can hold up to 8 valence electrons. And so those 2 extra electrons here can be put on that central atom. But now we don't have 3 things around the central atom, we have 4. So we went from 3, 120 degree bond angle, to 4. So what's gonna happen is now is I'm gonna redraw this whole thing. This thing goes away. I'm gonna place nitrogen in the center. I've got 4 things that go around the central atom. 1, 2, 3, 4. And we look at it and we go, oh, 4 effective pairs. You'll hear them sometimes called 4 effective domains, whatever, but we got 4 effective pairs. We've got a negative, a negative, a negative, a negative. That sounds very similar to what we did last video. 4 things around the central atom pushing away from each other. 4 things around the central atom. Connor. 4 things around the central atom. And now what do we have? With those 4 things around the central atom, this looks like it's going to be a tetrahedron. Now, it's not going to be in... Okay. It's not really going to be a tetrahedron. Have a good day, bub. It's not really going to be a tetrahedron. Sorry, my kid's leaving. It's not really a tetrahedron. It's a tetrahedron in terms of the electron geometry. We've got, if we just like, imagine we had like little magical goggles, and when we put them on, we only saw the negative areas. So if we put them on, you can see there's a negative area, negative area, negative area, negative area. And so imagine this guy once again, all of these would be the bond connected to a hydrogen, and this tall guy here, that would be my lone pair of electrons there. So what do we have is we say, oh, look at that. That's a tetrahedron shape for the electron geometry. But imagine I take the goggles and I turn a switch. And when I turn a switch, all I can see is those guys with the bonds. So I can't see that. I can only see the guys that are actually bonded to the hydrogen. Just pretend here, follow along. So I flip the switch, and all I see is that. Well, originally what I had was, I had nitrogen, lone pair. I had one guy come out to the side, one guy coming out to yes, one guy disappearing in the distance. And you go, oh, that's an electron geometry. If I just look at the negatives, that's electron geometry of a tetrahedron. But if I got rid of that guy, now what do we see? It looks like boop, 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 boop. It's a 3-sided pyramid. Kind of hard to see, but imagine you have a boop, 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 boop. And there's one panel in the back. That's a 3-sided pyramid, a 1, 2, 3. So what we'd say is this is a trigonal pyramidal. That is its molecular geometry. And so it has a a electron geometry of a tetrahedron, but it has a molecular geometry of just a three-sided pyramid. Now, with that being said, we would still draw its Lewis structure like that. One more thing to go with that. If you see these electrons are stretched out over this bond, stretch out of this bond, stretch out of this bond, they're going to cause repulsions. But if you see these two electrons are kind of smooshed down, they're smushed down here, so they actually cause a little bit more repulsion. There's more negative charge here. In fact, a lot of times you'll see people draw it like that, and that kind of represents there's more negative area kind of spreading out. So what you end up getting is these bond angles are not going to be 109.5, they're actually going to be 107 degree bond angles. And that's because this is causing more repulsions, which causes these guys to squish just a little bit tighter. So we have ourselves 4 effective pairs, 3 of them are bonded pairs, 1's a lone pair. The electron geometry of this thing is the electron geometry is a tetrahedron. The molecular geometry is a trigonal pyramid. It looks like a pyramid, 3-sided pyramid, trigonal, 3. 107 degree bond angle. Okay.